Subscribe to this YouTube channel by clicking the subscription button below. For future webinars and online short courses, please visit our website at australianwaterschool.com.au. Welcome to this Australian Water School webinar brought to you by iSwarm. It's a pleasure to have you all on board today. We're going to be discussing dam safety modelling using McBreach, presented by Chris Goodell and Craig Price. And I can see there's dozens of countries represented today. That's terrific. My name is Trevor Phillips. So today, two presenters, Chris and Craig. Chris is from Kleinschmidt Associates, Craig is from Surface Water Solutions. You can see from the text there that they've had decades of working water modelling. And in particular today, dam breach modelling. Chris, tell us, so where are you from? What drives you into this extraordinarily highly mathematical area of work?
Yeah, well, thanks, Trevor. Thanks for giving me the opportunity to present this. That's a really good question. What started it all was over a decade ago, doing a lot of dam break modeling and realizing, boy, there is a lot of uncertainty involved with the input parameters we're using here, and not really ever feeling very confident with the results we're presenting and what they actually mean. And so I saw a trend in several of the agencies here in the United States that were moving towards probabilistic methods, not just for hydraulic modeling, but for anything.
Yep.
And I thought, well, you know what? I wonder if we can apply this to dam break modeling. And so I started out like many people do with some spreadsheet models and kind of tested out some theories. And the next thing I knew, I had some software, and then I was doing projects. And
outstanding.
So here we are.
Outstanding, Chris. And you're up there on the west coast of USA, Portland, Oregon?
That's right. Yeah, Portland, Oregon. It's 3:30 here. So it's still got some daylight left.
Civil time for you, civil time for me, but not so civil for Craig. It's 6 a.m., 5 a.m. in Perth. We're from Western Australia.
Yeah. So no, all good here. I'll just kind of clarify on the roles here. I'm just going to be monitoring the chat line. Cool. Chris will be demonstrating his software.
Absolutely.
This is, but for the Australian audience, a lot of times we get lots of registrants from Australia and in this area of the world. You know, the Australian Rainfall and Runoff is asking more and more for Monte Carlo analyses, ensemble modeling, and you know, there's a great deal of interest in automating these processes so you don't have to sit there and code these things in one at a time. Now, Monte Carlo, when people hear that word, and especially when we hear about McBreach, this is not a Macca's, as they say in Australia, not a Macca's trend here. The MC for Monte Carlo is something that is, you know, you may want to look it up and see where it comes from. I think back on the Manhattan Project way back when during Cold War days, they were looking at ways of automating this sort of a computing power. And it actually, you know, just a little trivia bit, it is named for the casino, not the car. Some people have other things they use the Monte Carlo name association with, but it was a code name that was named for a guy's uncle who used to gamble away all of his money at the Monte Carlo casino overseas. So yeah, with that, I'm gonna just you know, step back and just watch the chat line. I'm very interested in this, and again, make a bit of a plug for our dam breach course. We ran it last year, about a year ago, and we had you know, quite a few registrants come in, and one of the things we didn't have sufficient time for was to get into the automation of the dam breach parameters. So this time around, 1 year later, we're running it again, and we've added an extra session for Chris to go through and introduce this software to you and allow you to use it on your own models and on our tutorial models. And so that'll be coming up in a few weeks' time. So I'm very excited to be able to offer that as part of our upcoming course.
No, absolutely. And wonderful to have such an outstanding duo here today, particularly Craig, to be there available. No further ado, I think we just jumped right into this now. We've got 1 hour, less than 1 hour, but we'll make this a fantastic discussion. Thank you for using the Q&A, everybody. Fire away your discussion points and questions, and Craig and Chris will be more than happy to respond. Over to you, Chris, or yeah, maybe Chris first. Maybe that's the best way to go. Okay.
Yeah, thanks again, Trevor, and thanks, Craig, for that excellent introduction, especially the little bit of background on Monte Carlo, because it is a little bit interesting and curious that this powerful computing technique was born out of gambling. But in any case, this is a technique used for not just what we're going to talk about today, but many applications from economics to science, and here we're going to talk about hydraulic modeling. Specifically, we're going to talk about dam break or dam breach modeling, as it's commonly referred to, and how we can use this software called McBreach to perform a probabilistic approach to dam breach modeling. This is something that I consider to be supplemental to our traditional deterministic methods of doing dam breach modeling, and I'll explain why as we go through the slides. So let's begin. And please, yeah, keep the questions coming, and I will do my best to multitask here, but fortunately I've got Cray and Trevor behind the scenes there, and they'll help out too as we go. All right, so there we go. So this is an outline of my presentation, moving towards probabilistic dam breach modeling. I'm going to go over real quick the state of practice. How are we doing this today? Essentially, it's deterministic simulations for the most part. Now there's people are moving into more probabilistic methods, not just for dam breach modeling, but for hydraulic modeling in general. And this is just one area where you can apply it. So I'll get into the uncertainty around dam breach modeling, which was really the genesis of me coming up with McBreach, was I was never comfortable with the large degree of uncertainty that you have in dam breach modeling. Then I'll go through the probabilistic analysis itself, including the automated Monte Carlo simulation. And that's what McBreach does for you. It actually automates this entire process. Now we can all, everyone out there could do this on their own, either through spreadsheets, maybe some macros, some simple scripts, but this just automates the process and makes it faster and easier to use. And that's the external controller, also known as McBreach. So I'll show you the interface there and how it works. Then I'll talk a little bit about statistical convergence, because Monte Carlo is really only powerful when you can demonstrate statistical convergence in your results. Okay, so I'll go through that for both the breach parameters and the output results. And then, of course, as some of you may already be wondering, how are we going to do Monte Carlo in a practical way with HEC-RAS models that take minutes, if not hours, or even days to run? And so I'll talk a little bit about ways that you can minimize simulation time and make this a very practical exercise. And then finally, I'll conclude with some remarks on moving towards risk-informed dam breach modeling. So let's take this dam for example. We have a dam here, and we've been tasked to do a dam breach simulation. Maybe it's to determine hazard classification. Maybe it's to determine the downstream inundation limits so that we can put together an emergency action plan. Maybe we're simply trying to quantify consequences. So how do we do that? Well, you might assume the breach happens over here. Maybe this is the deepest part of the reservoir. Maybe there's a known weak point, but maybe you don't know anything about any weaknesses in the dam, yet you still have to fail it in this exercise. Perhaps the failure would occur over here and be a little bit bigger. Maybe it takes a little bit longer to develop. Maybe the entire dam is washed away. We don't really know. Unless this dam has failed already and we're recreating a historic dam breach, this is simply a hypothetical dam breach. So we don't know how it's going to breach if it were to breach. And so we have to estimate it. And there's several techniques out there, but frankly, there's just not been a lot of research done on this. And one of the reasons is because fortunately, there haven't been a lot of dam failures, relatively speaking, over the years. And so there's not a lot of historic data to draw from to develop regression equations. So what we do is we come up with a deterministic assumption of the breach size, the shape, and the formation time. And there's some other breach parameters involved in this exercise, but this is the current state of the practice. We put together a set of breach parameters, and that determines not only how big and how fast our breach forms, but ultimately what is the hydrograph, the breach hydrograph coming out of the dam during that simulation. breach parameters in this case are typically selected towards the extremes or the limits of realistic ranges. And the reason we do this is because we want to acknowledge the uncertainty, not quantify it, but acknowledge it by using conservative assumptions. So conservative breach width might be, say, the widest breach width you can ever imagine. Maybe the entire dam comes out. And it used to be a common practice to not only remove the entire dam, but to try and do that nearly instantaneously when doing these breach runs. That's no longer used as often, but occasionally you see that. But either way, it's a very conservative approximation of what would happen if the dam were to fail. And so what we get breach hydrographs that are highly unlikely to be exceeded in magnitude. It's not likely that the peak flow that you see from your study would be equaled or exceeded if the dam actually were to fail. And this is on top of already conservative estimates of inflows. Let's say we're breaching the dam under a hydrologic loading. It's common here in the United States to use what's called the probable maximum flood. This is the maximum discharge or flood that you could possibly ever get in a certain watershed. And it's climatically driven, how you come up with this estimate. And so just by its nature, it's extremely conservative. But even the methods to determine this are purposefully conservative as well. And so you put that on top of the conservative set of breach parameters, and you're going to get a breach flow hydrograph that is very unrealistic. And that's typically what we do. But we sacrifice a little bit of that accuracy, or maybe a lot of that accuracy, to have some conservativeness and assurance that you'll never exceed that value. And there's definite benefit in that, but I think there's added benefit in understanding and quantifying the uncertainty and the probabilities of something like that happening. So here's an example of an inundation map that you might get from a breach analysis. This is what I would call a static or deterministic inundation map. It's a single map. It's produced by a single set of breach parameters. And presumably these breach parameters would be very conservatively selected so that they produce the highest peak flow and the fastest moving floodway. But here in this example, you see there are 4 properties, A, B, C, and D. Property A is outside the floodplain, and they're feeling pretty good about their house and where it's located relative to the dam. But properties B, C, and D are inside the floodplain or the flood inundation zone from this breach. What this communicates is whether you're in or out. It doesn't communicate any degree of risk. It doesn't communicate probabilities at all. All you can derive from this is, yes, I'm in the flood inundation zone, or no, I'm not. And that's not really a genuine way to present the exercise we've just gone through, this dam breach exercise. So the way we typically do this is we define a range of breach parameters from various sources. Okay, these sources may include regression equations. There's several of them out there for earth and embankment dams. There's rules of thumb that different agencies have come up with to help guide this process. Common sense actually plays a part in this as well, as does site-specific conditions. And so using all of these methods, you come up with a range of breach parameters. And to acknowledge the uncertainty, we typically will run a sensitivity analysis. So we'll have a set of breach parameters that produce the highest peak discharge and another set that produces the lowest peak discharge from a dam breach event. And just to round things off and to kind of make a more robust analysis, we'll add in a medium Q, which might just be an average of the two. That's our sensitivity analysis, but typically we'll just use the high Q set if that can fit this definition, which is the most conservative while still realistic set of breach parameters. This is language that's actually used here in the United States to guide us in how we select our breach parameters. Now, determining these or selecting these Sometimes it's through a collaborative process. You get a group of people together. It could be the hydraulic modeler. It could be the clients, maybe the reviewing agency. Everybody gathers together and they hash it out and come up with an agreed upon selection of breach parameters. But frequently, this is done at the discretion of the engineer or the modeler performing the analysis. And this is a little bit frightening because, frankly, you have one person who is deciding a very important thing, which is where will this water go if this dam were to fail? And there will be quite literally lives at stake in this case. So I think it's important to have this collaborative process, but I also think it's very important to maybe go to the next step, and that's what the probabilistic approach is all about. So what's the problem with the deterministic approach? I mean, you're picking the worst case scenario, so maybe it's not so bad. At least, you know, you can feel confident that it's not going to be worse and you're not going to have more flooding than you might expect. Well, here's the problem. Let's take 4 uncertain independent parameters and say these represent 4 breach parameters. Now, there's more than 4 in a HEC-RAS model. There's 10 to 12, I believe, if I recall. But let's just pick 4. And each of these 4 independent parameters represents a 5% exceedance probability, meaning we are confident that within 5%, these numbers won't be exceeded. Well, if you use that on all 4 of the parameters, that gives you a combined or collective probability of 0.0006%. And that's what we are presenting, something that is extremely unlikely to happen. Now, again, this may be, or I'm not doubting the usefulness of this, but it's not telling the full story. Okay, and again, this is in addition to all the other overly conservative parts of dam breach modeling. And really, you're not communicating risk and uncertainty in this approach, in the deterministic approach. You're either in or out of the inundation zone. You can't make risk-based decisions on this kind of a study. There's several different types of uncertainties involved. I'm going to cover some of these. And in fact, these can be grouped into different types of uncertainties. If you look this up, if you do some research on types of uncertainties, you'll see a wide range of different types. But for hydraulic modeling, I've grouped them into 4. We have statistical uncertainties. These are uncertainties involved with generating input values using statistical means or statistical approaches. This could be your inflow hydrographs for the upstream boundary condition. Could be stage hydrographs for the downstream boundary conditions. It could be other things, but in this case, we're using statistics to come up with a representation of what's coming into our model and what's going out. And there's some inherent uncertainty with those approaches. There's also algorithmic uncertainties. And this is simply the numerical scheme that the model that you're using uses. So how does it solve the equations? When we're talking about HEC-RAS and dam breach modeling, RAS will solve the Saint-Fanon equations, conservation of mass and the conservation of momentum. And there's an algorithm that's used to do that. And that algorithm comes with some error and some uncertainty. There's interpolation uncertainties. And this would be things like, let's say you've got a terrain surface and you want to use this in your model. You have to discretize that terrain surface, the continuous land surface, into cross sections or a 2-dimensional grid, or maybe both. And so that discretization of a continuous land surface introduces errors and uncertainties. And then there are just things that we don't know, knowledge uncertainties. For example, hydraulic roughness, like Manning's N values. We just don't know how to physically describe that precisely with computations. And that's why we have suggested values. We have these picture books where you can look at different types of streams and get ideas of different N values. There are equations out there to compute them, but they're all regression type equations. There's no perfect N value equation out there because We just frankly don't know how to compute that. Same thing with discharge and loss coefficients. And finally, dam breach parameters. And what I found when you're doing a dam breach model, the dam breach parameters are by far the most uncertain, the most sensitive input parameters that you have for your hydraulic model. So just to sum up the state of practice, it's by design overly conservative, often get very unrealistic results. There's no communication of risk. Okay, again, you're either in or out of the flood inundation zone. There's no way to assign probabilities of being flooded. And it presents a false impression of consequences from a dam failure. And that's what I really want to get away from, is this false impression. By producing this flood map, a lot of people will look at that and assume that's what's going to happen. But that flood map is actually incorrect. It's wrong. That's not what's going to happen. That's somebody's estimate, and usually an overly conservative estimate of what's going to happen. So how do we present a correct answer? Well, I would say you can't do that with a deterministic approach. The only way to be correct about this is to do a probabilistic approach. Okay. If you are here in the United States and you do any work with the Federal Energy Regulatory Commission, you may have come across their risk-informed decision guidelines that recently came out a few years ago. And in there, deep in the dam breach parameter section, you'll see a section that talks about probabilistic dam breach modeling. And here specifically, it says, in support of risk-informed decision-making, a probabilistic approach to dam breach modeling may be considered. Now, it's not shall be or will be considered. It's maybe, because it doesn't necessarily always apply. But in this case, it's kind of demonstrating that this is of value. This is something that can augment the deterministic approach. So what is a probabilistic approach to dam breach modeling? It involves a probabilistic risk assessment. And essentially what you're determining is a consequence given a condition. That's the definition of a probabilistic risk assessment. And when we're talking about dam breach modeling, we're looking at exceedance probabilities. That would be the consequence, an exceedance probability for a specific discharge. So in our case, the condition would be a dam failure. So we're going into this exercise already assuming the dam's going to fail. Now we know hopefully it will never will fail, but for the exercise, we assume the dam's going to fail. The consequence then is the peak discharge coming out of that dam, or the discharge, the breach hydrograph, you might call it. And then of course you can get a resulting flood inundation map from that hydrograph. Another way of putting this is, given a dam failure, what are the probabilities of exceeding specific breach hydrograph peak flows? So you would be able to assign a probability of exceedance to every single flow up to the maximum flow from the deterministic approach. So exceedance probability is determined through the Monte Carlo simulation by running many realizations. A realization is just a single modeled event in a probabilistic simulation. So you might think of that as a single HEC-RAS run. That would be one realization. Well, in order for Monte Carlo to work, we need to do many realizations. In fact, we need to do enough realizations to demonstrate that we have achieved a convergence in the statistical outcomes. So the way this works is you randomly sample the uncertain input parameters, and you do this about predefined probability distributions. Then you run a large number of realizations. I'm putting this number 10,000 out there, and I'll show you why in a few slides, but this gives you an idea right off the bat what we're talking about. A lot of realizations to do this for 10 to 12 degrees of freedom here. But we do this so that we can demonstrate convergence of the statistical moments of your outflow or your output. Once you've done this, then you sort all of the results, and that basically puts them into percentiles, which become your exceedance probability discharges. Now from there, you can decide, what do we want to publish? Which exceedance probability are we interested in? 10%, 5%, the 1% exceedance probability, or maybe even something a little bit more restrictive, the 0.1%. Really depends on you and your client, the governing agency, and a lot of it has to do with also what's downstream. What kind of consequences might we have if the dam were to fail? Alternatively, you can publish an exceedance probability inundation map. And this would be a map that shows several of these exceedance probability inundations in a sort of a contour looking map. So you would see the 10% inundation zone, you would see the 5%, the 1%, and the 0.1% all on the same map. Once you've decided what exceedance probability hydrographs you want to focus on, then you can route that downstream using your hydraulic model to determine the final inundation and consequences. Now, this is a relatively new concept for dam breach modeling. And so it's not well documented. There's not a lot of research that's been done on breach parameter uncertainty. There is some out there, but not a whole lot. And so what I usually recommend to people is you evaluate your breach parameter equations or your breach parameters using breach parameter equations. There's several out there, and we'll talk a lot about these equations in the dam breach class that Trevor and Craig both mentioned at the introduction of this webinar. So if you're interested in that, I'd encourage you to sign up for the class. But use those equations, knowledge of the site conditions, a little bit of common sense, and that can lead to really good approximations of the breach size and formation times, and more specifically, the distributions that you might have. Here you see a normal shape distribution, and that might be a good representation of your possible breach widths, for example, or maybe breach formation times. This is a normal depth example, but a normal distribution example, but you can also use uniform distributions. You can use log normal. Those are available as well inside of McBreach. Okay, but your job is to come up with expected values, which might be the mean, and the extremes, which might be plus and minus 2 standard deviations, or maybe plus or minus 3 standard deviations. It's really up to you to determine that. So this is all done, or can all be done, inside of McBreach. Here you see the interface for McBreach version 5.0.7. What McBreach does is it communicates directly with HEC-RAS. So if you have a HEC-RAS dam breach model already set up, all you got to do is go get McBreach and you're ready to do probabilistic dam breach modeling. So as you move from top down, this is kind of the order that you fill out the main window here in McBreach in preparation of your probabilistic dam breach modeling exercise. You would choose a sampling method. You can either compute or have McBreach randomly sample all of the input parameters, or you can specify them directly with an input file. Okay. Or you can go deterministic or probabilistic when we're talking about the breach parameters. So if you look down in the next section where you see all of these tabs across, you've got the breach invert, you've got the breach width, left and right side slopes, formation time, and all the other breach parameters here. And for each one, you can select whether you want to run them deterministically and provide your own number, or probabilistically and let McBreach randomly sample about the statistical distribution you provide. So if you do select probabilistic, then you set the type of distribution. Here's where you would select whether it's a normal distribution or a uniform or log normal or something else. And then based on the type of distribution you select, you have some input parameters to add. So here we see a normal distribution, and here you're going to put in, at a minimum, a mean and a standard deviation. You also have the option to truncate this distribution using an absolute minimum and an absolute maximum value. That way, if you do have some limits to how wide or how fast a breach may occur, you can set those. And a good example of that might be the full width of the dam. And you might assume we're not going to erode into the abutments. It was founded on very good solid bedrock, and so we're not going to erode into there. So that's going to be the absolute maximum breach width we could get. On the other side, you're not going to get a breach width less than 0. So that could be a logical absolute minimum. And then finally, you set the sample size. Here I've got 10,000 indicated, and then you hit compute. And hopefully come back in the morning and everything's done. And you've got your probabilistic distribution of results. So let me show you some a quick comparison based on 5 different data sets that I've done. And this is kind of a busy table, so I want you to focus on the very last row at the very bottom of the table where it says maximum. This is our sensitivity analysis for our deterministic approach. And on the last row, this is typically what you're going to publish when you finish your study and you write your report and produce your maps. The maximum value. All right, now look up about halfway down in the row that says 1%. That's our exceedance probability discharge for the 1%. And I've got that for all 5 different case studies here. Now, you compare that 1% to the maximum, and you can see the difference. The maximum is anywhere from 2 to 3 times larger than the 1% chance exceedance discharge. And that's a pretty rare or improbable breach results. And here it's already 2 to 3 times less than what we typically publish. So this just gives you an idea of what we're publishing versus what the probability of that actually happening is. Here's some examples of statistical convergence on the input value. So these are a few of the breach parameters. Here we've got breach invert elevation on the upper left. And what I did here is I ran a number of realizations. I ran a number of different Monte Carlo exercises, 10 different ones for that matter. And for each one, I did either 10, 100, 1,000, or 10,000, or even 100,000 realizations. And here you can see, if you look at the column for 10, you can see that I've got a widespread of computed means. But the more realizations I run, the more those computed means converge on a single value. Okay, you can see the same thing for breach width over here on the right, and even standard deviation shows a similar trend. And here you can see clearly why 10,000 is sort of a magic number. You can also, and should do this on the results, statistical convergence. So those were the breach parameters, but here shows an example of convergence of the peak discharges that were computed. And in this case, we're looking at only realization number 2,384 out of 30,000. But what you can see here as you go down, the third and fourth moments, statistical moments, have not quite converged yet. Mean and standard deviation look pretty good, but skewness and kurtosis still need some more realizations to show convergence. But if you run the full amount, in this case I did 30,000, you can see we get very nice convergence of all 4 statistical moments. So I'm going to pause here for a quick second and ask Trevor and Cray and anybody else, can you guys hear me, because the power literally just went out at my house and back on?
No, oh, really good. All clear. All clear.
All clear. Okay, good. I must
still hearing you.
Okay, good. I've got battery backup, and so
yeah.
Wi-Fi is still working, so good. Okay, I'll continue on.
You've done well. And thanks for the questions, everybody. We'll get to those questions in a moment. I won't break your run here, Chris. Keep going. Yeah.
Okay. Yeah. Great. So here we've got kind of the next step. So once you've run
You've got
summary of the results, and it's going to show you the 1%, the 5%, and all the way up to the 99% exceedance probabilities. And from there, you can actually pick out the breach parameters that that were randomly sampled to produce those peak flows. And then you can recreate that in your model and run the model again. This time we would run the full model versus a truncated version of it, and I'll explain what that is in just a second. Run the full model so we can map the whole thing. All right, so now I'm expecting any of you HEC-RAS users out here or out there to be thinking, how the heck does this work? How can we make this practical? When you're talking about 10,000 HEC-RAS simulations, when typically just one of mine takes not only minutes, but sometimes hours. And that's where we come up with the truncated model. Okay? And we're actually getting into a period of time where cloud computing and parallel computing is becoming a practical solution as well. So let me first talk about the truncated model. So the truncated model is going to be a version of your HEC-RAS model that focuses just on the dam and where the breach occurs. Because ultimately what we're running our probabilistic analysis on is the breach outflow hydrograph. So we really just need to focus on the dam, meaning we don't need the downstream portion. We only need a little bit of the downstream portion to provide a tailwater condition on the dam. We can get rid of the rest of it. And what that does is that not only speeds up your computations, but it can also remove a lot of the iterations that typically happen in a very dynamic model like a dam breach event. And so that alone can significantly speed up your model run. But you can also remove excess simulation time because we're stopping our model at the dam. We don't need the time, the simulation time it takes to route that hydrograph all the way downstream, at least not in the probabilistic exercise with McBreach. This also allows to increase our computation intervals as well, further reducing computation time. And then we can remove excess computation options, things that we just don't need for this exercise. For example, post-processing. For the RAS users out there, you recognize post-processing as being kind of the third step in your unsteady flow analysis. Well, we don't need that for McBreach. McBreach reads directly from the DSS file or the HDF file. And both of those are computed before post-processing. So we can eliminate that that time-killing exercise of post-processing. And here's an example of a full model on the left-hand side and a truncated model on the right-hand side. The full model is several kilometers long. The truncated model simply has the reservoir and the dam and a couple cross sections downstream, just enough to provide a nice tailwater condition. And for 10,000 realizations, that full model would have taken 13 days to run. But with the truncated model, we can do it in 5.5 hours. Now, 5.5 hours falls in the category what I call an overnight simulation. This is something where you can press the compute button, you can go home for the night, come back the next morning, and everything's done for you. And that was the other reason this thing needs to be automated, which is why McBreach is so important in this process. So here's another table showing you examples of some models where I've truncated and compared to the full model, and you can see the differences in runtime. If we look at Bear Creek Dam at the top, it consisted of 197 cross sections. The actual simulation time was 120 hours, but the compute runtime was 59 seconds in HEC-RAS. But when we truncated it, I got it down to 23 cross sections. I didn't need to run 120 hours because I wasn't routing this all the way downstream. Only required 24 hours, and that took 1.7 seconds per run. And you can see for the other ones, the last one there is actually a 2D model, and I truncated it from 31,000 cells down to 460 cells, and that reduced the time from, it's hiding a little bit, but I think over 2 hours to just 3 seconds. Actually, let me move this way. Sorry, 24 minutes down to just 3 seconds. So this is critical because if you want this to be an overnight exercise and you want to run 10,000 realizations, you need to get your individual realization computation runtime down to less than 5 seconds. So another option that's becoming more and more used and will be readily available for probabilistic modeling is parallel processing. You can do this in the cloud. Several of you have probably already used cloud computing. And this is a way just to speed up even a single RAS model. But when we're talking about 10,000, in theory, you could run 10,000 realizations all in parallel at the same time on 10,000 computation nodes and doing this in the cloud. And what we found in doing some prototype tests on this, that it can take an overnight exercise and reduce it to about a half hour. In other words, you can do 10,000 realizations in a half hour for any size model. Basically, that half hour is just the overhead time required to upload your model into these various nodes that you're going to be using and run it that way. I'm also very excited about HyperNet's Galileo product. This is a relatively new product that's out there. And what's really exciting about Galileo is it's not only an extremely intuitive and easy to use interface. Those of you who've used cloud computing probably know what I'm talking about. It's not a very intuitive service. It's hard to figure out. Galileo is extremely user-friendly, and for that matter, it's built for HEC-RAS. They've actually coded it to work directly with HEC-RAS. And so I encourage everybody out there, if you haven't discovered Galileo yet, go ahead and take a look. Get on their website. You can Google Galileo, HyperNet Galileo, and see what it's all about. And I think you'll be very pleased and surprised to see how what an awesome added tool this could be in your toolbox for HEC-RAS modeling. Very flexible. And in both of these cases, whether you're doing this on the cloud or through HyperNet's Galileo product, there's no need to truncate your model, because if we're running everything parallel, then we don't need the time saving required that requires a truncated model. So we've done this exercise, we've done the probabilistic approach, and now we've got exceedance probabilities for different discharges given a dam breach failure. We can plot those together on an exceedance probability inundation map that might look something like this. Now here you still see the maximum deterministic map, but we also now can see probabilities of being flooded. So now this tells a completely different story to properties B, C, and D, whom previously thought that they were going to be flooded. Now they know their odds or their probabilities of being flooded if this dam were to fail. And property B here all of a sudden doesn't look so bad. 1%, maybe upwards of 10%, depending on where on the property you sit. And so it's a completely different picture, and it's added information, and that's what this is all about. This is not about replacing the deterministic approach. This is about augmenting it, adding more information, adding more value to the work that you provide your clients. Here's an example of some sample breach widths from McBreach. And once you've sampled everything, you can plot these directly in McBreach, and you can see what McBreach ended up sampling. Here you can see this has been set to be a log normal distribution, not a straight normal distribution, which is why you see the extended tail on the right-hand side. This would be positively skewed. And here you can clearly see that it's following a very nice distribution. That's another way to test the convergence, is if you're following, if by plotting this in bins like this, you see the distribution shape that you selected, then you know you're doing pretty good. And then here we have peak discharges. So these are the results. And this is typical. You see this also tends to be skewed to the right a little bit, and that's because there is a lower limit. You can't get negative values for your peak flows, but in theory, you can go all the way up to the max discharge. But most of them will not be centered around there. So the expected results should be much less than your max discharge. And here we can see our expected, or our mean, is somewhere around 12,000 cubic meters per second. Whereas we did get some results all the way up to 29,000, but very few of those. Okay, and then here we have an example of several different breach hydrographs plotted on the same plot, both deterministic and probabilistic on the same plot. And you can clearly see the maximum or the high Q deterministic run is the peakiest one, or the tallest one. And then the very next hydrograph you see is the 0.2% exceedance probability. So that's almost half of the high Q, or the max deterministic run. So this just clearly illustrates in a nice figure the difference and the context of what we're producing when we use the max Q or the high Q for our deterministic results. Okay, so with that, that ends the presentation, but I want to point out that this software that I've been talking about called McBreach is available and it's for free. You can get this right after this presentation. Go to the website, or if you can't remember that, just search on McBreach, M-C-B-R-E-A-C-H. The software is available for free, as is the user's manual and example data sets that you can practice with. Now, unfortunately, because I am a consultant, I don't have a lot of free time to provide technical support. So that's one of the reasons we made it free. We wanted to not have you pay for something if there wasn't going to be technical support. And so you're kind of on your own, but there is some guidance out there, namely the user's manual, but there's also a discussion group on the RAS solution, which is the blog I host. So if you would like to get into a forum and ask some questions about McBreach, you can do that there as well. And with that, I'd like to thank everyone for attending. This is my contact information. If you have more questions about probabilistic dam breach modeling, including McBreach, I'd be happy to take those. And I think we have some time left to entertain some questions in this format as well. Thanks, Trevor. Chris,
an outstanding, high level of clarity for novice and professional. That's absolutely fantastic. I know we've only got 10, 15 minutes left here, but the questions are coming in thick and fast. What we've done is we've put the link to McBreach up on the chat line, everybody, if you want to go to that. Also on the chat line is the upcoming dam breach modeling online course and the HEC-HMS course, which we encourage you to come to. There's no way we can do justice to this topic. As you can tell, Chris has gone through it with a very steady approach. What I'm going to do is hand over to Craig. And Craig, are you okay to manage for the next 10 minutes the questions and answers on the Q&A line between yourself and Chris? That might be the better way to do this and faster way to do it too.
Sure. Yeah, what I can do is just mention a couple of the comments that have been addressed. I've taken about 10 of these that I've been frantically typing as Chris has been talking. I'll sum a few of those up and then just ask the questions to Chris. Yeah, let's get a few of these answered, because time is of the essence here. A lot of the questions that were answered already that you would not see already unless you go to the dismissed or answered ones have to do with like full momentum or diffusion wave, 1D versus 2D. Imperial units versus SI units. If you are interested in the answers to some of those, just have a look at the answered section. We'll talk a lot about sunny day versus rainy day and the combination. One question that I just wanted to mention, for example, somebody asked about earthquakes and cyclones. And yes, cyclones would be accounted for in the weather data, the meteorological data that you're going to use to feed into your PMP and your PMF for a rainy day failure. Yes, cyclones would be accounted for. An earthquake would be accounted for as one of the methods that, the things that might fail your dam for a sunny day failure. But putting those together, the peak flow of your PMP, happening at the same time as an earthquake, that's where you start getting into these really rare probabilities. So I just wanted to then just run a couple of these questions by Chris. Probably one of the questions here that I wanted to answer was which distribution? Was it normal, binomial, multinomial? Multinomial would be the most accurate for Monte Carlo.
Well, it really depends on what you're talking about, what breach parameter you're looking at. For example, when you're looking at breach widths, you might rightly assume that that follows somewhat of a normal distribution. Now you may say, hey, there's some limits. It can't go below this, or it can't be greater than that. And maybe there's something specific about the dam that would skew that one way or the other, in which case you may switch to a log normal distribution or something else. Where a uniform distribution might be more appropriate, and that's where all values, all sampled values have equal probability within your limits that are defined. That might be something like the piping elevation. The piping elevation, if we don't know anything about a weakness in a dam, but we want to simulate a piping event, we have to pick the elevation where that piping event begins. And not knowing anything about any weaknesses in the dam, you might say that all elevations or most elevations are equally probable. So a lot of it's up to you. It's up to common sense. It's up to site-specific conditions or conditions specific to the dam.
Okay, great. I think you're going to get requests here for taking your software and applying it to other models as well. I just want to confirm that this is just for HEC-RAS at the moment, and a lot of TwoFlow users would love you to be able to build this capability into some of the other software that people are using as well. But at the moment, it's just for HEC-RAS. Is that correct?
It is, but it can still be used to sample breach parameters. So it can still be a useful tool if you want to come up with a sample file of 10,000 different sets of breach parameters. And then it would be up to you to figure out how to automate the process of populating that in your particular model and running that and retrieving results. But it can still be used as a sampling tool. It's just not going to automatically run your software unless it's HEC-RAS.
And in a lot of cases in Australia, TwoFlow is very commonly used, and I see a lot of cases where the dam breach hydrograph is determined by these methods using HEC-RAS, and then the downstream flood wave is routed using whatever hydrograph you pick out of it in TwoFlow or any other software. It can
that's a great point, Cray. In that case, you could use HEC-RAS just to do the probabilistic approach, and then plug the exceedance probability hydrographs that you get out of this approach into your model of choice, whether it be TwoFlow or something else. That'd be a great application there.
Yeah. Okay. And then, Cameron's got a question here about the average breach width. This is a good one because sometimes it's not clear whether that's the top or the bottom. When there's a breach width, and we're talking about that, like your HMS using the base, in some literature it's the average. When we're talking breach widths, where are we measuring that?
Oh, are you talking about Cameron's last comment there about the piping elevation, or was there a different one?
No, there was a different one before that.
Oh, I'm sorry, I was reading the wrong one. Can you repeat that? I'm not seeing that one.
Oh yeah, so I'll just read it verbatim. Is the breach width the average breach width or the base breach width? Where HEC-HMS uses the base, but most literature derives the average.
That's right. So HEC-RAS uses the base, or they call it the bottom width. And so if you have computed average widths using regression equations, and you're right, most of the research out there does provide average widths. You just have to convert that to the base width.
Yeah, sounds good. Somebody asked the question: Would McBreach be acknowledged by U.S. authorities? You're going to get some official certification out there.
Well, I would say we're on the way there. It is acknowledged by FERC. I have used it on some FERC projects. They certainly have not mandated it as something that has to be used, but as I showed you in the presentation, it's something that may be used. And I would say if you want to use it, you're interested in using it, talk to your regional engineer at FERC and see if they're okay with that. The NRCS here in the United States is also interested in using it, and I've had some discussion with them about that. As is the Risk Management Center we're working with them to possibly incorporate this into their life sim consequence model. And so that's another kind of acknowledgement of acceptance there too. So, but yeah, it's still sort of in the infancy phase, and that's why one of the reasons I say this is not taking over or replacing the deterministic. It's an additional value added to your project. And I think you'd be very surprised at how many owners would be very interested in knowing probabilities versus just having a deterministic result.
Yeah, no, I appreciate that. And then it looks like we're just about out of time. The other questions, so we've got about 12 of them answered, a few open. Some of them we've just answered here live and didn't put into the text. But we will, Chris and I will both have access to these questions afterwards, and individually we can respond to you, so you're not left hanging. I did want to just make a plug here, just letting you know John Drexler is on the line and offered to answer any questions about Galileo. We'll put you in touch if you wanted to get into that and into further discussions. But go ahead.
Before you sign off, let me do just a quick fire on some of these. Some of these are very easy to answer very quickly, so I'll just kind of skim through and let's see. I'm looking at some of the ones that I can answer real quickly. We talked about McBreach independently of HEC-RAS. Is McBreach working using the 2D model? Yes, you can use McBreach with a 2D model. You just, if you truncate the model, you just truncate the 2D mesh instead of your cross sections.
One there also, Chris, about open source, Alexandra. Is McBreach open source? Can I include a module to vary the volume of the reservoir?
McBreach is not currently open source, and that's something that we may be discussing, but currently it's not open source. Let's see. So somebody had a question, George had a question about Monte Carlo or Latin hypercube as the sampling method or the probabilistic method used. And it uses Monte Carlo. I have not incorporated Latin hypercube. That is something that I would like to consider doing, but at the moment it's not there. I think we're out of time. So I'll answer the rest offline and we can get these posted.
Gentlemen, that's been an absolutely fantastic hour and a bit. And everyone, thank you for joining in and making it such a fantastic discussion on such a critical issue. All I want to say is thanks for participating. There's a feedback form coming up. The recording of this webinar will come to you via an email. There's 3 webinars coming up, you can see there, but I want to emphasize that yellow highlighted there, dam breach modeling coming up in 26th November and 3rd and 10th of December. 3 sessions. What we've done in 1 hour, we can spread across 6-7 hours in November and December. So do sign up for that via our website, and you'll see the links. Joel, thanks very much for your support today, and you can see Joel's put the links up on the chat line there. Well, I think we're just about there. And you had a power failure and your battery kicked in. Chris, all power. Go to the top of the tree.
I thought I lost everybody for a second. But
webinar presenter extraordinaire.
Yeah, there we go. All right.
I can't believe that. Yeah. Thank you, Chris. Thank you, Cray. Any closing comments? Otherwise, we'll sign off.
Sounds good. We'll see you in the course, hopefully.
That'll be fantastic.
Yeah, thanks everyone for attending. It's been a pleasure.
It's been great. Appreciate everybody coming and look forward to seeing you at the next webinar. Bye for now.
Okay. Bye-bye.
Bye.